Here's an equation. It would have a solution set with an infinite number of solutions. That's because there are two variables. The solutions would be ordered pairs. And we would typically express that entire solution set with a graph. Well, let's analyze the graph. What would it look like? Can we find some key characteristics of it? One way we can do that is by analyzing the graph in terms of any symmetry that it might exhibit, and analyzing the graph in terms of the intercepts. Where would the curve, where would it cross the x-axis, where would it cross the y-axis? Let's start there. Let's do the intercepts first. Remember, find the y-intercept. We substitute 0 for x and solve the resulting equation for y. And 0 squared is 0, so y equals -4. So the y-intercept of the graph of this equation's solution set is the point 0, -4. To find the x-intercept, we replace 0. We place 0 in place of y and solve the resulting equation for x. Well, this is a nice quadratic equation where the first power term is missing. We can just solve that using the square root property. X squared equals 4, so x equals plus or minus the square root of 4, which is equal to plus or minus 2. So there are two intercepts for the x-axis, the point -2, 0, and the point 2, 0. So our graph so far, we know, looks something like this. Intersects the y-axis down here at 0, -4, intersects the x-axis at 2 points, 2, 0, and -2, 0. And now perhaps if we learn a little bit more about it in terms of its symmetry, if it has any, we'd be able to get some rough idea of what the sketch of that graph looked like. Remember, to test for symmetry with respect to the y-axis, we let x be replaced by -x. And analyze this expression to see if it's the same as the original expression. And it is. The square of -x is the same as x squared, so those two expressions are equal. That tells us we have symmetry with respect to the y-axis. What about symmetry with respect to the x-axis? Well, there we replace, to test for symmetry with respect to the x-axis, we replace y with -y and see if we can get back to the original equation. Well, we cannot. If we were to multiply both sides of this equation by -1 so as to get back to y, multiplying by -1 here would give us y equals -x squared plus 4, which is not the same equation we had before. So this graph does not exhibit symmetry with respect to the x-axis. To test for symmetry with respect to the origin, we replace both x and y with -x and -y. This is equivalent to x squared and we're right back to the same situation. We can't transform this equation back into the original equation. So the only symmetry we have in this equation is with respect to the y-axis, which means if we find another point here, there must be a corresponding symmetric point over here. If we find a point that was here, there'd have to be the corresponding symmetric point there. And so the graph is going to look something like this, which I trust you already recognize was what the graph of that equation was going to look like. When we have y to the first power and we have x to the second power, that's our parabola. And in this instance, it's the parabola opening upward. So we can learn a little bit about the graph of the solution set of an equation by analyzing intercepts and analyzing symmetry.